You don't have to Okay, let's start the debate. I have so much to say about AGN that I cannot say it. At one of the conferences that we went to together, I gave a half an hour roast. Because how much history we got back together, how many anecdotes, amusing anecdotes he has. I'm sure Pablo can do even more than I can. Anyway, Doug is an amazing character. In the field of exosome pilot, he's one of the their papers, one of the first ones I read when I entered that field. And since then, he's even after I came into the field, he's continuously making all the waves all around, traveling around the world, irritating people. And finally, he retired. So I had to look up your whole list of areas you worked on, huge. So I don't even want to mention it. But after he retired, he continued to work because he just likes research so much. He said he's actually done way more research. Twice the productivity, he said, after retirement. I look forward to that. Good. Okay, so without further ado, and I do encourage you to come talk to him. He's such a great guy, so interesting, and he'll entertain you for hours on end. Here you go.
Thank you. Thank you, Angie. Okay, so I'm going to report to you something that has interested me when Pablo first came to Santa Cruz. And this was in 1990. And he came to Santa Cruz, he wanted to work on planets. Those days, there's only one planetary system. That's all. And so I said, Pablo, you will never get a job working in exoplanets. And let's work on something that may be more mundane. And so we talked about working on AGN, so my interest in AGN started with Pablo. And but then the exoplanets were discovered, we dropped everything. So it's time to go back to AGN. It's time to go back to AGNs because there's all this multi-messenger detection of AGNs and ranging from LIGO, JWST, many things are happening. So I thought we would just touch on some aspect of AGN. This is a big subject. It started about 60, 70 years ago when Lyndon Bell first proposed that the central engine of active galactic nuclei or quasars and maybe accretion onto black holes. And he developed some classic theory of accretion disk, which basically tells you that these black holes are surrounded by gaseous disks, which rub against each other to produce powerful radiation. What I want to talk about today is a little bit different from the classical picture, and still based on very similar things. What I want to talk about is stars in the center of these disks. This that contains stars, and whether stellar luminosity rather than viscous dissipation can power AGNs, and how the stars evolve in AGN disks, and what our observational constraints include, and what are the broader implications on gravitational waves, type of disruption events, and perhaps even the little red dots. So to start off with, and let's think a little bit about the boundary condition of AGNs. And there have been a lot of work done over the last 60, 70 years, and the Sloan Digital Survey provided a wonderful catalog of luminosity functions as a function of redshift, and you see that how this luminosity function of the AGNs evolved in time. From there, you can start to determine the Eddington factor and the efficiency factor of the most luminous AGNs. So the Eddington factor is basically the amount of radiation that will come out divided by the Eddington limit. the efficiency factor is the amount that you can convert the rest mass energy into radiation. So you need to know both the luminosity and accretion rate and the mass of the AGNs. But more than that, so I rely on the previous work and that has provided us basically with a kind of determination that these AGNs, they would accrete at a rate that is about 2 solar mass per year if the central black hole mass is akin to the 8 solar masses. So there's a whole literature of this kind of thing. Now, then I'm going to, just for comparison reasons, and I want to make some comparison with the classical accretion disk model and hand waving at that ad hoc accretion disk model called the alpha model. And if you have a steady state alpha model, you can write down this accretion rate, which is independent of radius, but it's a function of the surface density and viscosity. You link viscosity with some sort of turbulent alpha. And if you do this, and in a steady state with this accretion rate, and you can work out all of the unknowns about the accretion disk, such as alpha, which is the efficiency factor of angular momentum transfer, the aspect ratio of small h, and the gravitational stability parameter, which measures the possibility of gravitational stability, and you can work it out into a very simple set of equations, and you just need, that's one equation linking 3 unknowns, you just need to know about the 2. But if you use a standard alpha model, you find quickly that that describes energy dissipation very quickly. That you go beyond 100 RG to 1,000 RG, that the system becomes gravitationally unstable. Now, in these gravitationally unstable disks, it is possible for clumpy structures to develop, and Jeremy Goodman, well, actually, Yixian Chen, I'm working as a student with Jeremy Goodman and Yanfei Zhang, have looked at this structure and see the possibility that they form clumps, and these clumps may fragment and collapse into young stars. So I'll talk a little bit about young stars that will come out of this. There's another channel to produce young stars. That was some work that was done by Otto back in 1993 or so, and that is a possibility that if you have an accretion disk and the stars near the nuclear cusp may actually pass through the disk, and when they pass through the disk, there's a fraction of the star will experience sufficient amount of drag to get dragged into the disk. Once they're in the disk, they can accrete, and because the density in these regions are 6 to 8 orders of magnitude higher than the densest cores of GNC. So they can accrete and they can rejuvenate, become massive stars. So I'll talk a little bit about the fate of these, both of these paths, these mechanisms of producing young stars.
Can Pablo really get a job on that?
I don't think that was a job that he got, but but it was an attempt to provide the paved way. Yes, but there was some analytic, lots of analytic calculation. So now, so when we look at a disk, normally we think this disk generates heat because there's differential rotation. If you have a little bit of friction, you can get an energy generation rate from viscous dissipation. And if you have embedded stars, you can actually have the stars providing luminosity. And then, in addition, they may undergo supernova explosion, they can inject energy. And if they leave behind little black holes, they can accrete, you can release energy source. And finally, you have irradiation from a central source of different parts of this, and that can give you something, another source of energy, local source of energy. So in a thermal equilibrium, this Q plus is said to equal to Q minus. Q minus is the amount of heat that is lost from the surface of the disk. In a thermal equilibrium, you want to balance these. So today I'm going to focus primarily in the region of disk where it's dominated by stellar luminosity. And so in that sense, if you look at the stellar luminosity, then what you have is that the source comes from the surface density and some sort of luminosity. Of course, you need to integrate this with mass and all of that. You need to know something about the mass function. You need something about various things. Just writing down this for simplicity so you can see it in the algebraic form. Now, if these stars evolve off the main sequence, to maintain this thermal balance, you need to replenishment of young stars so you can work out, in some sense, the star formation rate, and basically, if you know something about the time scale of the star of the main sequence. Okay, so, but the stars inside these AGN, they are accreting continuous. They're not like the stars, even in Orion, Nebula, or any of these GMCs, because they're surrounded by such high density gas, they accrete. And when they accrete, they can actually gain energy as well. So in addition to the nuclear energy, you can have energy that comes from accretion, and they can produce winds that will carry away energy, so you can look at that. And the evolution, this just gives you a rough landscape, what are the physics involved here, and then I'll go into more details. So the mass change, the rate of mass change, depends on the accretion rate and the wind rate. Okay, so all of these involve physics. Now normally, we say, what's so difficult about accretion? But you're accreting in a disk, so the geometry of the disk matters. As we know, in the formation of gas giant planets in the protostellar disk. But in addition to that, in here, what is important is very often you accrete until you become very massive, then the intrinsic luminosity becomes sufficiently high, you can get close to the Eddington limit. So the radiation pressure can play a role to reduce, to balance against gravity, to reduce the boundary radius, to reduce the accretion rate, and you can have this kind of self-regulation. This is just a schematic illustration of what physics is involved. We go into details a little later. Stellar wind, of course, depends on the luminosity, that is radiatively driven, and we need to know something about it. The opacity, so the coupling between the radiation and the flow, and if you're very near the Eddington limit, then the relevant opacity for you to couple is really the electron scattering, which goes over wide range of frequency rather than line-driven wave. Okay, let's look at these details one at a time. And you will see throughout this talk, many of these processes are very similar to what you do in protostellar disks. And in fact, the students I've been working with, they work in both fields. So here is a 3D simulation of accretion of something like a embedded star in the disk around the supermassive star. And you can do this also with a planet like Jupiter. And you can do this 3D rendition, you'll find that, in fact, most of the flow from this is where the planet is, and the radius goes from this way, and the this way, and most of the flow comes in the neighborhood of the planet from midday, even though there's something coming in here, there's hardly any density mass flux come from here, and you can do the latest addition of 3D to D comparison to see things like accretion rate and things like whether they migrate, type 1, type 2 migration, whether there are changes in this asymmetry, and it's linked to things like whether they go through outward or inward migration, etc., etc., etc. And you can also work concurrently for M node. So that provides us with some guidance on the accretion rate. But what is different here is this question that there is a lot of radiation coming from below because there's nuclear energy generation, and when you get to massive, they're very close to Eddington limit. So you have, on the one hand, material wants to come in, on the other hand, there's radiation pressure that's coming out, and so this is a genuinely 3D problem, and how the inflowing gas interact with emerging radiation. And when I originally wrote this thing, it's linked to 1 minus lambda squared, and the simulation provides a justification for that kind of approximation. Xie Chen and Jiang Yanfei have done this type of simulation. Okay, so now we have a picture of accretion coming in and wind goes out. The next step is what happens inside the star. Okay, if you have a supply of material that comes in, and if this material is thoroughly mixed with the star, and then you have a wind that carries away the nuclear ashes. You can have hydrogen comes in, hydrogen-rich material comes in with some helium debris as they go out. You can actually have metabolism. So this metabolism will tell you that these stars can live forever. They become the immortal stars. They can grow to several hundred, up to 1,000 solar masses, very massive objects for the person who just came in. And you can actually grow them, become this kind of asymptotically limiting immortal stars. So that's one channel. Now, all massive stars usually have some sort of radiative envelope that separates the convective core from the exterior. So if this separation can occur, as we have shown from this type of simulation earlier, you can have this region that has a radiative core that separates the outside from the inside. Then what you find is that the inside can get isolated, then you will have an evolving star. Go back to the evolving star. Even though the mass of the star can be maintained or can get up to about several hundred solar masses, but then this core will start to get enriched in helium. As the core starts to get enriched in helium, the mass luminosity relationship shifts. And that shifts as a function of the stellar mass and also as a function of helium production. So if the helium abundance increases all the way to 1 unity, close to unity, then you will see that the location for different y value, the mass luminosity relation changes over like this. And these are the result of Mesa model. Now, if you now see where the mass luminosity relation crosses over the Eddington limit, you find that these are the asymptotic masses you should get. But this quantity of how close you get to the depends on this coupling between the radiation and the gas flow. So if you change this by a factor 2, only by a factor 2, and you will find already that this cutoff mass can change by the order of magnitude. The reason for it is because these massive stars, their mass-mass relationship is almost like an Eddington limited function. Okay, because that the core is burning at the rate that is almost Eddington. So they both they're parallel to the Eddington mass radius relationship. So they're very close to mass to the power 1, and as a result, if you change the helium content a little bit, this equilibrium mass would be reduced by a lot. So if you have an isolated core and the envelope from the exchanging envelope, and as the helium increases, the equilibrium mass very quickly declines. And that decline will lead to, that decline is a gradual decline. So if you look at the mass accretion rate, you get to this peak region, and in the evolving stars, their helium is enriched in the core. So as a result, they start to shed mass, and as they shed mass, they come down on this track. Whereas the immortal stars stay up here because they're exchanging their fuel, and they're getting rid of the ashes. So they have two very distinctive outcomes. Now, what are the implications of these outcomes? So there's two sources of helium. One is the source of helium that's in the disk already, okay, and one source that is inside the star, that's constantly being generated. If you have an evolving star, and if you start out with a disk with very, very high helium, you don't grow very much before you start to decrease again. But if you take solar value, you get up a couple of hundred solar masses. So these sensitive model dependence are taken into account, and you can work out from this relationship. This is very rapid rise, because this is just initial only growth to this equilibrium mass. Equilibrium by equilibrium, I mean that the accretion rate and the wind rate start to balance. Okay, so these are all very theoretical concepts. And so how do you actually create inside this turbulent gas? In this turbulent gas, turbulence is constantly being generated. And so if you try to look at the interaction between this accreting object and the surrounding region, you get two types of process. One is the important process, is whether they migrate or not. And this undergoes sort of stochastic migration for those who are into the protostar accretion process. And what that means is that the orbit of the embedded planet will move back and forth, and they drift over time scale, long time scale, so they don't go very far away. The second point associated with this is that the turbulent gas will feed the embedded object with random orientation, spin of it, random orientation. So on the eddy turnover time, the total amount of mass you accrete is not that much, but it accumulates over long periods of time, and the angular momentum is back and forth, change all the time. So these objects, they may have relatively low spin because the material they create have very different orientation. So that will come back. We'll come back to that point later. So now we talk a little bit about the evolved stars. Evolved stars. This is actually very different.
Can I ask a question?
Yes, yes.
So, You're setting it up as a stochastic process. Is that a fully defined set of kind of Laplacian equations with no
Yes.
certain?
Yes. We have a potential function that generates the turbulent spectra that looks like a common spectra. We match all of the quantities, the turnover time scales. We compute the evolution.
Can you calculate with ultra high resolution micro?
Yes, that's correct.
And that works well? Just
That works very well.
Kind of seeing,
Yes, we try to model this very precisely. Because this is also a very important process in planet formation in terms of driving resonant capture, release, and various other things. So now I'm focusing right along. Instead of looking at the evolved star, the immortal star, I'm looking at the evolved stars. Because these stars actually accrete and shed. And like the standard case, these stars never get into the red giant, even when their mass in center, when their helium content in the center dominates the whole process. Okay, so we will try to evolve this first with Mesa code, and then with a post collapse calculation. So along the line, we can calculate with Mesa code the elemental distribution inside the star, and especially near the surface. We can also work out the accretion and the wind rate. So from these quantities, we can work out the return or the depletion of various heavy elements. Okay, so the heavy elements, we look at it in 3 stages. One stage is the stage between the onset towards the peak, and then to the peak mass, and one set is from that point down to the helium depletion, down to the hydrogen depletion. Finally, we look at the case that is in the post-helium depletion stage. So here were 3 different, these are the main sequence stage. Okay, and what happens is in the main sequence stage, if the disk has a solar composition, then what happens is that on the main sequence, the primary burning process is CNO. So you get helium enhancement, and this is standard that everybody knows. Okay, in the post-main sequence, you get reduction primarily of oxygen, and then a very little nitrogen, and then so on and so forth. Okay, and after helium depletion, and you can have carbon burning, and you can have all the way up to silicon burning. At this point, the alpha element, the Mesa code breaks down. So now I'm going to make some comparison with observation. What are the implications with observation? When we look at AGN, and the AGN signature is very prominent, especially with broad line reading. These lines are broad, easy to measure, with strong signatures. And some of these AGNs are at very high redshift, and they are full of these very strong lines, and nitrogen, carbon, and oxygen, and magnesium, and so on and so forth. Some of these lines are bland, and you have to be very careful that the strengths of the lines are determined not only by the abundance, but also by the ionization fraction. So you need to use Hauge to analyze the metallicity from these lines. So we look at the lines. There are 2 types of lines. There's the broad line region, and that's presumably from the disk very close to the supermassive black hole, and the narrow line region, presumably either from the outermost region of the disk or from the close galaxy, and we can make a comparison. Through the line ratios, we can start to deduce the metallicity of various components. Helium, carbon, and these are the alpha elements, nitrogen, quantity, and iron. And the first thing you notice is that, hey, look at this. These are the blue lines. The blue lines are the broad line region. The red lines are the narrow line region. So the broad line region are systematically more metal rich than the narrow line region in all different elements. That tells you perhaps there is some sort of source in situ that's actually generating heavy elements. Okay, consistent with this general picture. Now, some of these lines are very high. For example, here is factor 3 lower, and there could be, in some cases, nitrogen even get up to 5, or 5 is plus minus a few. Helium, on the other hand, has not increased by very much. But of course, some of the helium is come from primordial helium, the Big Bang helium. You subtract that off with a little bit extra left, and again, you don't get to be significantly supersolic. You get a factor, maybe factor 2, but the disk is not dominated by strong helium composition. Now that's important.
Why should the narrow line region have stars breeding and growing and moving?
Probably because of stuff, well, I'll come back to that.
Okay.
So let's look at the alpha element again. Now this time as a function of redshift. Now what you'll find is there are a number of surveys, and each one of these surveys has their systematic bias, slightly different bias. Okay, so you can see that there are all these analyses, and they have some spread. But by and large, what happens is if you follow the same analysis, they're all supersolar. The same analysis also tell you they're essentially independent of redshift. They're basically, it's not a strong function of redshift. This is completely contrary to everything we know about chemical evolution of galaxies. When you go to high redshift, it's supposed to be very metal poor, and low redshift is supposed to be very metal rich. You should have a very steep function like that. That is flat. Why is that? Well, let me first explain that why this, what I just talked about, the independent redshift, is because the material you actually pollute the disk. And the disk doesn't stay here, it goes down to the black hole. So it actually flows towards the black hole, the junk gets dumped down there. Okay. The second question is, as Ching asked, why is the narrow line region has less metal than the broad line? It's because the broad line region is here, narrow line region is here. So this is like the mountain of Colorado. There's a chemical plant and there's a fertilizer plant. So you have a fractal gradient, and you can calculate this in terms of standard diffusion coefficient. Okay, with the source term, which you work out from your model of AGN with the protein number of stars that needs to be formed, and then you can work out gradually as this moves along. Okay. Now let's look at, before I look at iron, I want to come back to this question of nitrogen. Okay. Now the nitrogen nitrogen is important because the nitrogen is a secondary product. So you need to have already one generation before that produce the alpha elements primarily in the form of oxygen and carbon. Now, in the standard stellar evolution in the galaxy, this takes some time. And today we know already that in an ratio of 10, nitrogen is very much enriched. And it starts to challenge whether we can do this with the standard pathway of generating nitrogen. But here, we have a generation of stars that with evolution time scale is a few million years. And they pollute, and then they use up their pollutant and to produce the next generation. And so you can actually generate nitrogen very quickly. Today, this morning I received a preprint about this object at 14, redshift 14, with very strong nitrogen, and something like that. Maybe that. Now look at iron. So these.
They get other elements for redshift 14.
Say it again.
What other elements do they get?
Oh, there are several other oxygen and some other element. I can show it to you.
With alpha rich.
Alpha rich. And so here is iron. So now we can compare iron over magnesium, and then you can use this as one way of identifying whether there is core collapse, supernova, or type 1A. That means supernova A, and most of them tells you that these systems are more like type 2 and core collapse supernova. So associated with the reduction, we can actually produce this kind of picture. How do we do it? So the MESA model gets me to the onset of silicon burn, then it crashes. Okay, so I turn to Chris Fryer and ask Chris Fryer, how do we go beyond that point? Because now the core is about to collapse. So he said, oh, we have these calculations and models that we can do, and beyond that collapse, can you give me an estimate of the angular momentum content of this residual core? So that's why it was relevant for us to calculate the angular momentum, the amount of spin, and during that collapse, you form a little disk around the black hole, and then in this disk, the density temperature is so high, you get into equilibrium, massive amount of iron production, and then you have some jet flow. And so this is a little bit the kind of model people produce from gamma ray bursts. And we apply this model and then try to see whether we can generate adequate amount of iron. And the answer is we can. And associated with that collapse object, there are always the production of a few solar mass black holes. Okay. So I think this is just a post-collapse calculation with the angular momentum, spin distribution, and then try to work out both the production rate from the disk, which is the wind, and then holding back the collapse envelope. And from there, we can generate things like various elements, including magnesium, silicon, and various other things. And this is work that is continually being upgraded as we're generating more models and these values, which is just an example. They're not yet being compared with observation. But that's very rich comparison to be done. Okay, so I think look at this. Let me just briefly categorize these two channels, this two track. One track is that you have fully mixed, or not fully mixed, actually, extra mixed. It's an extra mixing between the convective core and the informing envelope and the radius thrown in between. And if you can mix that artificially, and then you have immortal stars because the material coming in can refresh the hydrogen supply and the helium goes down. So you only pollute helium in the disk. You never evolve of the main sequence. You don't produce alpha elements. The evolved star separates into the burning core from the envelope. The core starts to use up all of the hydrogen, turn it into helium, and then you shed some of the envelopes, and then you start to have onset of triple alpha, burning alpha element generation, and various other things. You have helium in heavy element production, and you end up also with a black hole. Okay, so this is a general picture that bifurcates the two tracks, and today we think from these hydrogen enriched bromine region is probably the evolved stars, what we call the CITA stars, in stellar evolution and pollution model. Okay, so what are the implications with the little black holes? The black holes is produced and it can start to re-accrete again. But it's accreting from this disk, which is excited by radical turbulence. So the turbulence will, the turbulent gas will feed back onto the star. As a result, the angular momentum of the material you accrete from, the spin angular momentum goes up and down. Along the way, the mass accumulates, and then the angular momentum is suppressed. This is the random Hall process. This is relevant to the LIGO sources, because they all have very low spin angular momentum. Now, so far I've talked about standalone individual stars. What we want to know is how many stars can we produce so we can actually maintain enough energy from the stellar evolution to balance against the surface cooling. So this surface cooling this time is basically the heating from stellar evolution. Okay, and you can work out all of this, and then you find that at any given time, up to about 1 parsec, you have several thousand coexisting massive stars, all are nearly happening when they form. So this raises the possibility, perhaps we can actually have the possibility of interaction with the disk, and between the different stars, and they can start to collide, coagulate, and grow. Now, these are the first set of hydro simulations that's done by Hui and among others. But this kind of brute force simulation is not all of the story. So this just simulate evolving and just dynamics without any consideration of what goes on the inside of these stars. So let me move on to show that we can do an alternative. We can actually do things with embodied simulation with a prescribed gas energy. Then this problem is very much similar to what is called oligarchic growth or planetesimals. And you actually start to grow these embryos because they collide with each other. So we will ask the question, how frequently do they collide, and what happens when they collide? So we can work out from the standard estimate collision frequency at the merger rate, and we can work out the merger timescale. And the merger timescale seems to be actually very interesting. And you see, if you're at 1 parsec region, and this timescale is half years, but the moment you get to 0.1 parsec, you start getting half a mega year, which is actually short compared to the stellar evolution time. Okay, so in the lifespan of a star, you can actually have multiple mergers. So what happened to these mergers? So when you have these mergers occurring, okay, and then their luminosity goes up. So what the first thing you do is you make their helium content. If you make their helium content, and then you can work out it's going to be somewhere between the two stars, helium abundance. So they will kind of reestablish their their accretion wind equilibrium mass. So they will shed off some mass, and the shedding of the mass will lead to a decrease in the total luminosity from the stellar population and lead to a generation of new generation of stars. But it is also possible that this merger timescale is actually faster than the wind timescale, because if I go to, instead of 0.1 parsec, I go to 0.01 parsec. 0.01 parsec is 1,000 gravitational radius. There are stars this is already gravitationally stable. It is at that location I will find that before they can shed off their mass, they have another merger, which means that they can actually go through runaway accretion. This is where you can get very massive stars produce the inner edge of the system. But this is still needs to be investigated further. Now, I talked about star-star merger. But there are plenty of black holes that's generated from these population. In fact, there's 10 times more black holes that's generated at any given, at any time than there are massive stars. Because the time scale for generating them is short compared to the duration of the black hole, a supermassive black hole, AGN active phase. So you can actually capture, you can calculate the capture rate of black hole into the star. Now, the black hole into these masses are not the same as the Sorensky-Gauss objects. Sorensky-Gauss objects, the neutrons are around low mass star. Here is around high mass star, over a couple hundred solar mass star. So the star is already near Eddington. So if you send in the black hole to the center, as is accreting at the Eddington limit, you're actually not generating extra luminosity. And so the mass, the gravity and the radiation pressure is essentially balanced. So detailed calculations are being underway. We're trying to look at the structure of this type of system with black hole. Is the time scale to sink to the center integration? What about the possibility of more than one black hole comes in? Then you can have a second black hole comes in. Okay? In fact, the time scale is the merger time scale with the black hole population. Now, if they can get close to the center, they can capture each other into binaries with separation comparable to one solar radius. And you can actually pile up multiples if you can wait that long. But the binary black hole can actually undergo gravitational radiation. They undergo gravitational radiation. You can work out the time scale for them to merge, the possibility of producing gravitational waves, the recoil in this environment, and you can look at the population as a whole. Clearly, this may be linked to LIGO events. So you have LIGO events with this type of picture we associated. It's in space, two black holes come together. This channel is in the heart of a massive star. So I think this is very exciting to utilize the LIGO event, gravitational wave events, to explain AGNs, not the other way around. So let me wrap up, so I run out of time. Okay. As you can see, AGN disks resembles photostellar disks, and they form and trap stars. Trap stars can be rejuvenated in mass evolved into supernova. And dead stars can provide energy input to heat the AGN disk. And we can actually measure this type of heating process at the SED of AGN, and also by microlensing dissection of the luminosity on the surface of the AGN disk. Evolved stars may pollute AGN disks to super solar metallicity at redshift 10. And that metallicity is independent of redshift. Supernova leads to the production of iron and few solar mass little black holes. These little black holes can grow substantially by either accretion or merging with each other. There are two different channels. Ultimately, the measurement of the channel difference, which one is the preferred channel, will come from the black hole spin. Because when the black hole accretes gas, gas is accreted randomly, so the spin orientation cancels out. But if they actually merge through merging process, they gain by they merge with bodies of comparable mass, their angular momentum will be larger. So, and they can either merge and they can shed mass for the stars, and they can undergo runaway growth, and maybe forming relatively massive intermediate mass black holes. C black holes are retained, they will migrate and capture dioxide. I already talked about that. Single and multiple C black holes and could be inside the star. But more importantly, I think that at the end of the day, that maybe the dormant AGN is surrounded by many of these residual little black holes, and these residual black holes might have some implications on the tidal disruption rate. I think I will stop there, and answer any questions.
Along the way, questions? Let me ask, I'm actually not sure, you didn't mention CITA migration timescales of stars. Is that an issue? If you're at the Worldline region, how long does it take the stars?
Yeah. Okay, so the embedded stars is not an issue because they're surrounded by so many other stars that are perturbed by each other, they're perturbed by the trigger. So they go through random.
You never get.
They never
They never get trained into the.
They never get driven. The turbulence is strong, so they can move and then they can change direction, and then they go back and forth.
What would be a normal business time scale?
The normal viscous time scale is probably 6 to 7 years. The viscous time scale, this whole thing is about 10 to 8 years long, but there may be additional supply from the outside.
So you have to resist.
Yeah, the one way to think of it is aspect ratio. We know. We also measure, by the way, from reverberation. The aspect ratio is about a few percent. And we can measure that, and it's consistent with this picture. Oh, the more massive objects, the very massive object, if you have a runaway, or if you have intermediate mass black hole, then what happens is very decent. And this I never mentioned, is that the massive object would undergo two-body relaxation with the surrounding cluster. So they undergo dynamic friction, interaction, they migrate towards the black hole. They push the residual disk gas into the black hole. So that, I think, is what determines the AGN lifetime.
So the relationship of this to my favorite object, very massive object, or BNB agents, etc. Given and black stuff was this kind of special region in the center. And then it was as if you had a lot that could happen in between a envelope and that core. But I didn't understand what the physics of that was.
Okay, so let's go back to
Really simple.
this picture,
Yeah.
right?
So what exactly is that interior glue thing?
This is a connected nuclear burning core. Okay.
And the white surrounding?
This is supposed to represent the radiant layer, the radiant zone.
So,
Okay. If you manage, so this region is the region you can have exchange with this gas, because you have a region you have. The question is whether you can penetrate through it.
well, there's lots of interesting convective overshoots.
Yeah, well, that's the point, right? That's the uncertainty. That's why we're doing both type of simulations. We're doing both connected with an artificial mixing and without. And then the answer to that is that if I have this overshoot mixing and all of this, this star becomes immortal because there's fresh supply. This is not the same as your standard standalone stellar evolution. This thing is embedded in a glass background. So if you manage to mix, then you bring fresh supply to the nuclear burning core, where CNO burning is ongoing.
And train it all the way in.
Yeah, if you penetrate all the way in. So that's exactly why we want to understand how fast can we spin.
Right.
And-
So just going back to that for a second, so when we did some work with our net, we had a really interesting situation where an entire envelope lifted off,
Yes.
associated with overshoot,
Yes,
and the Woosley crew, they got something slightly different. What they showed
yes,
is how precarious the issues are effectively associated with the region you're talking about.
yes.
And so, the problem with that is, you can't use Maisie for that.
Yes, well, there is some detailed physics that we have not addressed. We merely say, if you have mixing, what will be the consequences? If you don't have mixing, what will be the consequences? The actual physics exactly what determine the efficiency of mixing, we don't say. What all we can say is that these stars are unlikely to be spinning fast.
Yeah, but the conclusion you're coming to is that even very massive stars can lead to black holes between a few solar masses as opposed to
Yes,
the much bigger.
yes, that's correct.
So, are you really confident in that?
I'm absolutely not.
Any other questions? Yeah.
You should know that. You should always take it with a grain of salt.
We always find upstairs. Any other questions before we? No? Oh, please. Go ahead.
So when two black holes are in the disk of a very large mass body, you set some basic equations like which mass is growing fastest and what to judge what the evolution.
Yeah, you could do that. You could do that. The problem is that if you try to merge two black holes in the disk, the time scale is huge. And the reason I want to put inside the gut of the star is the density in the gut of the star is of order unity, not of order 10 to the minus 12, 10 to the minus 10. So that is much faster way to bring the two of them very close together. Of course, we have a binary inside there, and how they agree, and will be determined by the Roche geometry and all that. Except in here, once you get into that environment, the time scale for them to go merging is actually short compared to the mass doubling time, and less efficiency factor is well below 10 to the minus 2. So you can agree that the cell-meter time scale can be very short. If the cell-meter time scale is not very short compared to the merging time scale, And you got there, you're done.
Okay, well, let's thank the speaker and then. I don't.
I just, that's it. It's different from the center, so. They kind of agree.
But the top 20 doesn't so high.
Oh, no, they just make some adjustments. And you do make some adjustments because of the radiation pressure. They have to expand that a little bit. Yeah.
I mean, only a little bit. You say that academic mass is so much greater.
Yeah, it's not as great as a nuclear energy.
In particular,
Because it's self-regulated.
large
Yes.
regions,
Okay.
very
It's not
slow.
significant. But low mass is not.
Low mass we can always expect it. Low mass I can always expect it. So you can only do this. Yeah.
He basically tells us.
Yes. Yes. So I hope it's not too much.
Oh, no, no, in fact, let me introduce Seeley.
Yeah.
He's joined